Hey gang, welcome back for another video here on JoChem. Okay gang, so if you're coming from the intro to amino acids video and you're hungry for more, you're in the right place. In this video, what I want to talk about is the amphoteric nature of amino acids and based on the conditions, pH namely, that you put an amino acid in, how it can look different from a charge perspective, right? Positive and negative. Okay, so if we take a look at this lovely structure right here, if we take a second to look at it, the R group is just a methyl group. We know this is alanine. And if we take a second to realize, right, this is the first priority, this is the second priority, this is the third priority, we're going in this direction. We look R, but our hydrogen's facing towards us. So we look R, but we're actually S. This is S-alanine, right? Okay? Just a little review from the last video. Okay? So, if we take a look at this, there's no charges going on here because that's how I've drawn this, amino acid. However, we know that this amino acid has the ability, particularly at this point, to produce H+, and this amine right here is basic. So this has the ability to, I would say, pick up H+. Right, so we are amphoteric, and that is the case with amino acids because they have this basic component and this acidic component, okay? So what's interesting is the whole basis of this video is that if you have this amino acid, right, in certain conditions, if we have this, in a place where there's H plus abundant, right? This is absolutely not just going to be NH2. It's going to be greedy. It's going to pick up H+. This amine is going to be in a protonated state. It will be NH3+, right? And, right, we have this COOH, and if the conditions are right for the carboxylic acid, right, if it's the strongest acid around, it's going to do its job and donate H+. So what you will see commonly, amino acids be drawn like this in a charged state. And we'll get more into it, right? But when you have an amino acid that looks like this, and you have equal amounts of negative and positive charge, you have what is called, and this is my favorite word in organic chemistry, a zwitterion, okay? That's when all the minus equals all the plus, right? So if we have 1 and 1, we have a zwitterion. If you have 2 and 2, you have a zwitterion, right? So that's pretty cool. Now, obviously, we haven't really discussed anything concrete. So, what I like to do, the best way I feel like this was explained to me, what I'm going to do is, I'm going to erase this. So let's just picture, so this H right here, right, let's just say this was fully protonated. Let's just say we were at pH, 0. At pH 0, this hydrogen, this proton, has a rough pKa. It's around like 2.2, okay? So I think the best way to explain this is at pH 0, there is other acid stronger. Like let's just say we have this S-alanine in a solution of pH 0. Since this acid, I like to think of it as this acid right here can do its job up until pH 2.2. So if there's a stronger acid around, if we are below pH 2.2, something is going to protonate this right here. This H only leaves, and we only get a negative charge when we are above pH 2.2. So essentially, what I like to think of is at pH 0, our whole structure is protonated. If we start to raise our pH, so let's say we just get to like pH 2.5. At this point in time, we have gotten to a point where the strongest acid around is the carboxylic acid. So it will now have a negative charge. Nothing happens with our side chain, but that's where we're at. Because we've now reached the point where the most acidic hydrogen, right, at pH 2.5 is the proton in the carboxylic acid, right? It can kind of do its thing when the pH is above 2.2, right? Your S-alanine starts to produce H+, so we have a negative charge. Now here's the thing, right? Let's keep upping the ante, let's keep increasing our pH. what you'll see is the pKa, here, I'll do this. Whoop. The pKa for NH3+, right, is roughly around like 9-ish. It varies based on your situation. So this won't lose a proton and become NH2 until we've kind of reached over the 9 pH mark. So let's just say we get to pH 10, for example, or even 12. Let's just really make sure we've nailed it. At pH 12, there's going to be something around, or we're moving towards a less and less acidic environment, right? Because our pH is going up. So even though this isn't a great acid, it eventually can start to do its job and produce H+. And that's the point where we get NH2 and then COO-. So you can see, based on our pH, we can be at a place where we're either positive, negative, or a sweet spot where we actually get our Zwitter ion, okay? So you can see that at various points, things will either be protonated or not protonated, okay? So we're gonna get into more like, how do you determine this? But for the situation where and things can change if your side chain has acidic or basic components, but when you have something like S-alanine, for example, where your side chain doesn't play a role whatsoever, very commonly you will be asked to find this point, and it's not this exact pH, I use that as an example, but you will be asked to find the part where the solution is equal parts negative and positive with your amino acids. That is called, like there's a certain pH point called the isoelectric pH. It's at this point, I think the name almost explains itself. It's where roughly because this is dynamic, right? You're constantly, it's not like, okay, every amino is plus, every carboxylic acid is minus. It's constantly, things are getting protonated, getting deprotonated, right? It's where you reach this equilibrium at a certain pH where you have roughly zero net charge, where all of the plus and minuses cancel each other out. That's what the isoelectric pH is. When you have no side chain that influences, like if you have no, acidic or basic components in your side chain, your isoelectric pH is just the pKa of the carboxylic acid proton plus the pKa of the NH3+, the protonated amine, divided by 2. So it's like the average of the two. So that's super straightforward to find out. So for example, I'll actually get some concrete numbers here. I don't have concrete numbers, but so and you can, and this is PI. You can, right? So let's just say for alanine, let's say the pKa for the carboxylic acid is 2.2. Let's say the pKa for the amino group is 9.1. I just make it easy math, 9.2. Then your isoelectric pH would be 11.4, 5.7. Hope I did that math right. Right? Because you'd have 11.4 divided by 2, and that's how that goes. Right? So if you need to find the isoelectric pH, that's how you do it. You get the lowest pKa, which is going to be that of your carboxylic acid. You get the highest pKa, which is going to be the pKa of your protonated amine group, add them together, divided by 2. That's your isoelectric pH. The pH where in that equilibrium, the net negative, net positive is 0. Okay? But obviously the more interesting part is going to be what happens when we have side chains that are factors. So let me erase this and then we'll discuss. Okay, gang, now that we talked about how to calculate the isoelectric pH when your side chain doesn't have any acidic or basic component involved, I want to now look at what happens when you have an acidic component to your chain, and then we'll talk about what happens when you have a basic component. And if that first part was a little rough and maybe you are thinking, I didn't quite understand that, don't worry, because when I first was introduced to this topic, I was kind of frustrated. I thought to myself, I understand acid-base chemistry, but I'm having a little trouble grasping this. But I think once we do this example and then the next example, it'll become much more clear, okay? So if we're looking at this amino acid we're gonna look at now is aspartic acid. And as the name suggests, right, we have an extra little bit of acid in our side chain, okay, in our R group. So what I've done so far is I've just identified the protons that we're looking at. I've labeled their pKa values. And more importantly, what I want to do is kind of take the pH elevator, is what I'm going to call it. We're going to start from the ground floor up. We're going to start at a super, super, super low pH, where we're super acidic and everyone's protonated, which is what we have going on here, right? We have this carboxylic acid with a low pKa, it's protonated, and we have this carboxylic acid, it's protonated, and we have our NH3, which is protonated, right? Okay? So I'm just going to say, let's just say this was pH 0, okay? We're super acidic. No one here is the strongest acid, right? Something else in our environment is much more acidic and has protonated everything. Now what I want to do is I slowly want to crank up the pH. So let's just say this is our solution now has a pH of 2, okay? Right, so maybe at this point, and again, this is not precise, I'm kind of eyeballing this, but I want to just show the exercise of what happens when you start upping your pH and you start, the solution starts eclipsing pKa values. Your solution starts to get more, less acidic, and the different acids or the different protons on your amino acid can actually start being produced, and you start getting negative charges at your neutral sites or neutral at your positive sites, okay? So at pH 2, right, let's just assume that this carboxylic acid can start to do its job. It says, if when the solution starts to get less and less acidic, it starts to think to itself, hey, I can do my job. I'm the strongest acid around now. I'm gonna start producing H+. So we have more than just this one molecule of aspartic acid in our solution, but what you can start to see, or you would see, is obviously the amino group with that much higher pKa value is not gonna start producing H+, but the carboxylic acid here will become a carboxylate, okay? And obviously nothing exciting going on with our hydrogen here, and not yet anything going on with the side chain here that makes this amino acid aspartic acid, okay? So I'm gonna draw a dotted line, and we're gonna take our pH elevator up another floor, okay? So let's just say we crank this pH up to 4.5. I just wanted to pick something greater than this value of 3.7 right here, okay? So at that point, right, and I'm not equating pKa's and pHs, but I'm assuming at this value, we would start to have this carboxylic acid start to do its job, okay? So, right, nothing changed with this carboxylate because clearly it has already been donating H+, so we have a negative charge there. The amino group is still, again, it's the weaker acid, right? The solution needs to get less acidic for this to start producing H+. Obviously nothing happening with our hydrogen, but it's at this point that the side chain will actually take on a negative charge. Okay? There we go. All right? So now let's take the elevator up one more floor. Let's just say our solution gets much, it's getting more basic, it's getting less acidic. Let's say we're at 11. Just made it up. At this point, right, the amino group says, okay, I can finally join the party. I'm now qualified to start producing H+ because I'm a strong enough acid to do. I say strong enough meaning relative to the rest of the solution, right? Relative to the rest of the environment. Okay. So now it would go from NH+ to NH2. We still have a negative charge there. We still have a negative charge here, and hydrogen is just still hanging out. Okay. So now, what did we learn, right? That was a great exercise. What did we learn? Well, kind of two things. We see how this amino acid can look at various different pHs, which is also a question people can ask you on exams. Someone might be able to say, what does aspartic acid look like at pH 5? And they would label these, protons with their pKa's, and you'd have to understand, okay, at pH 5, these two acids can do their job, produce H+, the amino group can't, so I would have two negatives and a positive, okay? That's like one question. how does the amino acid look at a given pH? The second question would be, what is the isoelectric pH? And remember, we talked about that when your side chain is boring, bland, not a factor. But here, we don't just have two sites, right? Before it was just your amino can be positive and this, carboxylate can be negative. You average the pKa's to see where they cancel each other out in your zwitterion. But now we have three sites, okay? So at this point, right? So there's gonna be a point. It's at this point when this, right? Like we can't have both of these producing H plus because then we don't have a balance of charge, right? And we need to strike the point where kind of this is doing its job and this is not doing, and this is not, producing H plus, and this is like about to produce H plus, if that makes sense. So the way that shakes out is when you have an acidic side chain, you take the two lowest, you average your two lowest pKa's, right? So here, what that means is we would take 3.7 plus 1.9 and divide by 2, right? Because those are the two lowest. We want to find the point where we kind of need to average out where, we have these add up to one negative charge, if that makes sense, right? We can't have them both be negative because then it would be two negatives and one positive, but we need to get a combined -1 from here to then have this, to that counterbalance our plus and get our zwitterionic behavior, right? So the PI, the isoelectric pH of this is 2.8. I've never seen a situation where someone would make you memorize the pKa's for various amino acids. I'm sure they'd be given to you. But you definitely need to know how to evaluate and rationalize how a given amino acid will look at a certain pH, okay? So remember, with your basic side chain, take your amino group, take your carboxylic acid, add them together, divide by 2. If your side chain is acidic, take your two lowest, right? Because you need to make sure that they combine to have a -1 overall. That counterbalances your positive from the amino. And what you're gonna see is, I'm gonna clean this up and we'll talk about basic side chains. It's the opposite. We're gonna take the two highest. So give me 1 second, we'll tackle this and call it a video. Okay gang, so now that we've talked about side chains that don't have any acidic or basic components, and we've talked about side chains with an acidic component, I wanna tackle how we determine not only what the structure looks like at various pHs with basic components in the side chain, but I also want to talk about how we also determine the isoelectric pH as well, okay? So if we look at this, again, I'm just trying to incorporate previous things from the terminology from the first intro video, but if we take a look here, this is lysine, but since we see the amino on the left-hand side of this Fisher projection, we have L-lysine, and because this is not cysteine and it follows our nice rule, I can already tell this is S-lysine. If you don't believe me, break out your stereochemistry knowledge and test me, okay? So if we take a look at this, right, we can see that we have definitely two basic components, one of which is in our R side chain, okay? So unlike the previous example with aspartic acid, we need to find PI, and what we're going to see is that we're going to basically average our two highest pHs. But let's take the pH elevator and see how we look at different pHs and rationalize why that makes sense. Okay, so this is pH 0, right? Something basically just at a super low pH, a super acidic conditions, we have everybody protonated, okay? So let's start cranking the pH up. So if we look at pH 4, for example, something high enough to where we don't even question that this carboxylic acid has started producing H+, we will look like this. Oh man, okay. I say oh man just because I know I'm gonna run out of space. Or I wisely did not, that's okay. So what I'm gonna do is 1, 2, 3, 4. I'm gonna abbreviate this. I'm gonna do CH2 and say I have 4 of them. And then this down here. Okay, I hope that abbreviation's cool. Just basically, I'm just abbreviating the 4 carbons right there. Okay, So at pH 4, it's easy to tell that our carboxylic acid has become carboxylate. It is producing H+, so we have a negative charge. So you can see that we're not really at we're not nearing an isoelectric point yet, or an isoelectric pH, right, or point, because we have 2 positive charges and just this 1 negative. So once we start to approach where this is starting to, we need this to kind of to be neutral, right? We need an equal amount of, negative and positive, okay? So let's look at something like pH, at pH, let's look at like 9.8. Okay? So at that point, we've eclipsed this at that point we have eclipsed this point where the amino group here is going to look around in the environment and say, think I'm strong enough to start producing H+. So that will take, the NH3 down to an NH2, which is neutral. So our Fisher projection will look like this. I'm not gonna give myself enough room. COO minus H. This becomes an NH2, and I'm actually gonna lower this down a little bit, just to give myself some room. CH2, we have 4 of them. And we still have this NH3 as a positive charge, okay? So, you can see that at this point we're neutral. So maybe the isoelectric pH, is somewhere in that neck of the woods. So let's even continue to make our solution less acidic. Let's make our pH like 12. Let's make it convincingly to the point where this amino group is gonna get deprotonated. It will start producing H+, okay? So I have my COO minus, we have H, we have this being an NH2, and we have this 4 CH2s, as well as this will now be NH2 because it has realized it could, at pH 12, it could be strong enough relative to its environment to produce H+, knocking it down from it being positive to neutral. Okay, so at this point, right, we need to, for the isoelectric pH, we need to kind of find the sweet spot where this is still positive, but this has been, deprotonated, if you will. So it's like the protons that matter, right? With the acidic side chain, it was the 2 lowest because we knew we were going to have the 1 charge always there, and we needed to figure out where we were going to maximize the point where we were neutral. With the basic side chain, we need to worry about our 2 highest pKa's, not the 2 lowest. So here we would be averaging 10.5 plus 9.0, divide by 2. So the PI, if we do some nice little mental math, or I look at the paper where I've written down, 9.75. Weirdly, mental math gets really nerve-wracking when you're doing it in a room, when you're taping by yourself. Okay, so gang, I'm gonna clean this up. I wanna write 3 bullet points and do a little video recap. Okay gang, just to tie this video up with a pretty bow, if we're trying to determine the isoelectric point for a given amino acid, right? If your side chain is bland and boring, it has nothing basic and nothing acidic in it, just take the pKa of your carboxylic acid, the pKa of your protonated amino group, add them together, divide those suckers by 2, that will give you your PI, right? Now, if you have an acidic component in the side chain, right, remember, we're thinking about the lowest pKa's, right? So we take the lowest pKa, we take the second lowest pKa, add them together, divide by 2, and then for basic components, do the opposite, right? We're worried about the higher pKa's, right? So take your highest pKa, take your second highest pKa, stick them together in your calculator, divide by 2, you'll get your isoelectric pH. And if you need to, if someone maybe asks you, like, what's aspartic acid look like at pH 6, right? Do what I think the way we did the analysis made the most sense. Start with everybody protonated and slowly up the ante and up your pH. And then just watch the protons fall off and then get to your target pH that you're evaluating and then see who's, see who's still protonated, see who got deprotonated, okay? I hope you feel more confident determining isoelectric pHs as well as evaluating how amino acids look at various pHs after this video. So thank you for liking, watching, and hopefully subscribing. And no matter what, I'll see you all in the next video.